We're going to talk about words and morphology. What are words? It depends on what?
A lot of things. Like a word in Mandarin is not going to be defined as the same as a word in English.
Probably not. Or maybe it is possible to come up with a universal definition for a word, but certainly not like something that's translated. Like if you're translating English into Mandarin, it's not going to have the same number of words, whatever those words are. What is a word? So it's like there's a smaller unit than a word, which we'll find out about today, which is a morpheme, which is the smallest meaningful unit in a language. But words are sort of the smallest standalone unit, the smallest unit that can stand by itself, themselves. Well, what is morphology?
Study morpheme.
Not really. Not really. But it involves morphemes.
Like how words change when they're used.
So that's part of morphology, yeah. It's about the internal structure of words. We'll talk about that in a minute. In fact, we'll talk about that now. So we're going to start off with a little bit of a disclaimer. One complaint that we often get in this course is, why are you always talking to me about linguistics? I'm a computer scientist. I don't care about linguistics. I don't know about linguistics. Well, the fact is that natural language processing is not just natural, it's not just processing, it's not just P, it's also NL. And just as you would need to know something about biology in order to do computational biology, it's helpful to know something about language and how languages work in order to do natural language processing. If you were linguists, we wouldn't have to talk to you about any of this because you would already know. So we're talking to you about it precisely because you're not linguists. And we're hoping that you'll see its relevance to the things you'll learn about that relate more specifically to the computational side of things. So what is morphology? Well, it turns out that words are not the smallest unit. Words are not atoms. Or words are like atoms in the modern sense instead of like the ancient Greek sense, right? Because they're, for Democritus and ancient Greeks, it's like atoms were the smallest thing that you could get, and you couldn't get any smaller than that. Well, words are not like that. Words are more like the modern conception of atoms that are made up of subatomic particles like electrons and neutrons and protons, and these might be made up of smaller things like quarks, and you got your gluons, and you've got your, so just like a modern atom, words have internal structure. It's easy to forget this if your native language is English or Chinese, because English and Chinese don't have very much morphology. But even in these languages, words have internal structure. So you can take English words like misunderstandings, and you can really divide this into 4 or maybe 5 units. So you've got understand, that's the root of the word that gives it its basic meaning, and then you've got miss that makes it negative in some sense, ing that makes it into a noun, and s that makes it plural. So this word has internal structure. Even in Chinese, which has very limited morphology, you still have morphology. So here's an example. You have 同志们. So 同志 is actually morphologically complex itself because you have 同 meaning shared or common, and 志 meaning like cause. So 同志 means like to have a common cause, right? Or it means comrade. And there's this thing, men, in Chinese that's mostly used with pronouns, but can be used with some nouns to make them, some nouns for people to make them plural, right? So you can have, you can add men to 同志 and get 同志们, comrades, except it doesn't really mean comrades anymore, right? What does it mean? It's not that funny. You're bad people. It means like gay people, right? 同志. 同志们. So there are different kinds, the meaningful units that you put together to make words, like miss and understand and ing and s, or tong and zhi and men, are morphemes. You have different kinds of morphemes. You have roots that carry the main meaning of a word, and then you have affixes you add on to roots to add information or to change the meaning or to change the part of speech. So you can have prefixes, suffixes, infixes. So these are not very common in English, although we have some of these that are, we have one kind of infixation in English that is productive, and it's called expletive infixation. Basically, you can stick like fucking, inside of a word, and to make it mean, have a deprecatory meaning. So you can talk about, I drove from Pennsylvania to California, and I'm so fucking tired, or something like that. And then you have circumfixes, which you stick around the thing that you're attaching them to. We don't have much of this in English, but in German, you have this circumfix that's used to form sort of like the past form of verbs. It's not exactly that. So sammel is to gather, and gesammelt is gathered. There's also morphology that doesn't involve concatenating things together, that actually involves changing things in various ways. So in English, we have umlaut and ablaut. Umlaut is like when we change the vowel to make it plural, like foot to feet or tooth to teeth. And ablaut is when we change the vowel in a verb to change the form of the verb, like sing, sang, and sung. Now, there are some languages that take this sort of thing to the extreme, somewhere between this, between umlaut and ablaut and infixation. And these are languages like Arabic and Hebrew. Anybody here speak Arabic? Anybody speak Hebrew? Or read Hebrew? Nobody? Usually there's somebody who reads Hebrew, who went to Hebrew school. In these words, you start off with a root. It's usually like 2 or 3 consonants, and then you shove vowels in between those consonants and before and after in order to form different forms of a word or in order to change the meaning of the word. That's called root and pattern or templatic morphology. And it's challenging from an NLP perspective, actually. And then you have infixation. But perhaps more importantly, there are functional differences in kinds of morphology. So there's a difference between what's called inflection and what's called derivation. Inflection just gives you different forms of the same word based on the context where the word occurs. So examples of inflection are things like number, like singular versus plural, or case, like nominative versus accusative case in languages that have that, where it changes depending on whether a noun is the subject of a sentence or the object of a sentence. We have that for pronouns in English, but not normal nouns. So it just makes different forms of the same word, like different tense forms, different number, different case. That's all inflection. Derivation either changes the meaning of a word or changes the part of speech of a word, or both. So it creates new words with new meanings or new parts of speech. So taking parse and creating parser from it is an example of derivational morphology, or taking repulse and forming repulsive from it, as in my professor is repulsive, that is derivation. So why is this important to NLP? Well, let's say you're building a search engine and you want people to type in search words and to be able to retrieve documents based on these terms. Do you want to just search for the literal words, or do you want to do something more clever? You say more clever? What do you want to do? So you want to search for all of the forms of a word, right? So what do you want to normalize out? What do you want to get rid of, basically, if you're doing information retrieval? Which kind of morphology? You want to get rid of derivational morphology? You want to get rid of inflectional morphology, right? Because that just makes different forms of the same word. But derivational morphology can change the meaning of a word. And you don't want words that are completely different in meaning or that are substantially different in meaning. You want words that are, you want to search for different forms of the same word. So this is an important distinction. And in your homework, as it happens, then you'll be writing lemmatizers, programs that take different forms of verbs, in this case, and return a lemma, a basic form of that verb. So all of them get normalized to one form, all of the different forms of a verb. And it's dealing with inflectional morphology. So one of the problems of morphology that makes it challenging to work with is it tends to be kind of irregular. It can be irregular in form, so we have a difference. Sometimes we have verbs like walk, walked, walked. And sometimes we have verbs like sing, sang, sung. And it's hard to predict which pattern you will get. It's very annoying. It's also the case that there's semantic unpredictability, particularly with derivation. So you have this ly suffix, but it means different things depending on what you attach it to. So you could say a kindly old man, but you can't say a slowly old man, even though kindly and slowly are both perfectly good words. So this is semantic unpredictability. So morphology can be kind of annoying because it can make words that are the same seem different. So for information retrieval and sometimes information extraction, you have to sometimes get rid of inflectional morphology. But it also provides sometimes useful information that can be of value to certain tasks because it provides information about relationships between words, about the grammatical role of words within sentences. That could be useful in things like machine translation and natural understanding and semantic role labeling. We'll skip that. So, well, we'll not entirely skip that. So some people think morphology in NLP, if you're willing to do it in a rule-based way, is kind of a solved problem. We know we have good tools for doing rule-based morphology and NLP. And it's one of those areas where it's actually sometimes easier to write a rule-based system than to annotate a whole bunch of data and train a machine learning-based system because of the way that morphology is relatively constrained. But there are a lot of people working right now on neural approaches to morphology, both supervised and unsupervised approaches. That is, approaches that use labeled training data and no labeled training data. We won't talk so much about those directly, although a lot of the same issues apply. So let's talk a little bit about levels of analysis. So you can take a single word and you can view it from different perspectives at different levels. So at the bottom here, we have the surface forms of words, what you actually observe in text. At the top, we have an analysis of these words into a lemma, hug, panic, fox, and into a set of features or properties that each of these words has. So this one is a verb, it's progressive. This one is a noun that's plural or a verb that's singular. And to get between these two levels, then we have an intermediate level, an intermediate form. And this is one where each of the morphemes has exactly one representation. And we also represent morpheme boundaries with a caret and word endings, word boundaries with a hash mark. So we can imagine translating hug plus verb plus progressive into hug, and then this ing, which is the progressive marker, and then translating hugging in hug-ing into hugging with the double G. So we'll learn, in your homework, this will be very important. We'll actually not do this exact process, which is called morphological analysis, where you go from the surface form to the lexical form, but we'll do lemmatization, where we ignore this. That is, we ignore the plus verb plus prog part and just go from hugging to hug-ing to hug. So given an input hugging, we want to generate hug. Given an input panicked, we want to output panic. Given an input foxes, we want to output fox. That's basically what your homework is about, except you go both directions. Does this make sense? So you could imagine just doing it directly, but actually that's a lot harder. It's much easier if you have this intermediate step, because then you can separate concerns. You can separate the concern of how the properties map onto morphemes from the concern about how the spelling rules, the way you write things, affects the surface form. So we're going to do this with finite state transducers, or FSTs. Who here has heard of FSTs before? Somebody raised their hands and then said, no, I haven't heard of FSTs before. Yes, you've heard of FSTs?
Yeah, we did it in college.
Oh, okay, that's true. We did do them in college. So who's here heard of FSAs, finite-state automata? Hopefully many more of you. So FSTs are a generalization of FSAs where each transition can have two labels rather than one. It can have an input label and an output label. And we'll talk about that relation in a little bit. But basically what FSTs do is they define relations. They define regular relations between strings. These are widely used in practice, not just for morphology, but for morphological, not just for morphology, but also for speech applications, for surface syntactic processing. In fact, I was talking to somebody today who works on the Alexa team in Pittsburgh, and we talked about how they use FSTs to do intent and domain identification. It's widely used in Google for morphology, but also for surface parsing of queries and other things like that. So they're used. On the other hand, they're not really a research area. So if you go to an NLP conference, you will not hear papers for the most part about FSTs because they're so well understood. Everybody already knows basically all of the properties of FSTs, and people can use them, and they're great. But to understand FSTs, it's helpful to first understand FSAs, or finite state machines, which should be familiar to a lot of you from theoretical computer science. So let's talk about them briefly, just to make sure we're all on the same page. So a finite state automaton consists of Q, a finite set of states, a state Q0 in Q that is the special start state, a set F that's a subset of Q that's a set of final states, and sigma, which is a finite alphabet. Now, what is an alphabet? I always have, I'm very pedantic about this, actually. Is A an alphabet? Is Z an alphabet? No, what are A and Z? They're elements of an alphabet. They're letters or symbols or characters, but they are definitely not alphabets. So an alphabet is a set. It's a set of symbols. So you have sigma, a finite alphabet. And then you have transitions between states. So here's a state, and there's a transition between them. I shouldn't do that because there are people who are watching and they can't see me pointing. So it's very rude. But you have Q sub I and Q sub J, and between them you have a transition that has a symbol on it that's drawn from sigma. So basically what it does is it encodes a set of strings that can be recognized by following paths from Q0 to some state in F. So here's an example. So for you who are wise in the ways of finite state machines, can this machine recognize the string BAA exclamation point? Yes. What about BAAA exclamation point? Okay. What about BA exclamation point? No, because you start at Q0, you have B to Q1, you have A to Q2, but there's no transition with an exclamation point from Q2 to a final state. In fact, there's no transition with it labeled with an exclamation point. So it rejects that. So will this accept a finite or an infinite number of strings? Infinite. Why is it going to be infinite? Because we have the loop, right? So this corresponds to a regular expression, doesn't it? What regular expression does it correspond to? So B, A, star, exclamation point. In fact, all finite state automata correspond to regular expressions. And all true regular expressions have a corresponding finite state automaton. So sometimes people get confused. They So we talk about like tracing our way through a finite state automaton, and they ask, well, can it see ahead or look ahead to where it's going? How do we know if there's an ambiguity and you could go more than one way? How do you know which way to go? This is due to a problem in pedagogy. So we talk about these procedurally, but they're actually not procedural. These are a mathematical construct. They're a description of a relation. And if it helps you, think about it in terms of depth-first search. So you're applying depth-first search to look for paths through the machine. Let's skip that. So the set of languages that can be recognized by a finite state transducer or a finite state automaton are what are called the regular languages, as in regular expression. And they're basically equivalent. So they're weakly equivalent. So for every finite state automaton, there's a regular expression. For every regular expression, there's a finite state automaton. You who use regular expressions a lot, and I hope there are many of you, I love regular expressions, but if you use Python, you might have a distorted notion of what a regular expression is, because Python regular expressions are not actually regular expressions. They are more powerful than regular expressions. What could Python regular expressions do that you could never do with a finite state automaton? Back reference. Yeah, back reference is impossible with a finite state automaton. You can't see backwards. You only know what came before by what state you're at now. So you can't do back copying or back reference with an FSA. And that's not part of real regular expressions. But it's convenient, and so people add it to their regular expression implementations, starting with Perl and moving up to Python and JavaScript. And it's convenient, but it also means your implementation of regular expressions is slower because you have to use a less optimized algorithm for doing it. So this is kind of a shorthand depiction of what a finite state automaton that recognizes English derivational morphology might look like. So it's shorthand because for noun I really corresponds to a whole bunch of transitions. And in fact, each noun, you have a transition for each letter, basically. So this is really oversimplifying things. And the same way for the suffixes, then you really would have a transition for I, for Z, and for E. But that gets very messy, depicting it visually. So to make it simpler and easier to understand, your textbook depicted it in this way. So this brings us to FSTs, or finite state transducers. So the idea is to be able to do morphological parsing and analysis and morphological generation. So for parsing and analysis, or for lemmatization, you start off with a word. And the output is the words, the stem's lemmas and features expressed by other morphemes. For you in your homework, it's just going to be the lemma, right? The basic dictionary form of the word. So there are three ways that you could do this. There are at least three ways that you could get from a word to its analysis. What is a table, a lookup table? What are the advantages of a lookup table for a task like this? You can hash it, and you can have fast lookup. So what's the disadvantage? It's big, takes up a lot of memory. You're kind of out of luck. If it's out of vocabulary, you can't do anything. So what about a trie? What advantage would a try have over a table? Yeah, so you search for by the prefix. So the advantage is going to be, it's going to be flexible in some ways. Could you elaborate further? So is it going to be as big? No, because all the redundant information is being crammed into part of the representation. Is it going to have the same out of vocabulary problem as the table? Yeah, it is. Because it can just store stuff. It can't calculate new stuff. So a finite state transducer is small, relatively speaking, relative to a table at least. Not necessarily much smaller than a try, sometimes bigger. It doesn't have necessarily the out of vocabulary problem because you can write a finite state transducer that will infer what the lemma is and pair off the suffixes or the affixes that for the derivation, the inflectional morphology. And that's basically what you'll be doing on the homework. So we'll talk more about that. So finite state transducer is it's just a generalization of a finite state automaton. It's just the same, except instead of having one alphabet, you have two alphabets, an input alphabet and an output alphabet. And every transition has two labels, an input label and an output label. And it works just like a finite state automaton, except that you have, instead of having one input tape, you have an input tape and an output tape. And every time you cross a transition, you read from the input tape a symbol, and you write this symbol to the output tape. Now, an important thing to know is these symbols can also be epsilon. Epsilon is the empty string. So this is how finite state transducers do insertion and deletion. It's by either substituting things for the empty string or substituting the empty string for symbols. So why might this be useful? Well, let's take an example from Turkish, an extreme example, but a real-world example. So Turkish is notorious for having very long words with lots of morphemes in them. In fact, there's this word, uygarlaştır ama diklar imizden mişsiniz kasına. Does anybody speak Turkish here? Okay, good. So this means behaving as if you're among those who we were not able to civilize. You've already seen this example, right? So Turkish actually has lots of words like this. Not all of them are quite this extreme, but it has you can freely form new words by combining morphemes. And this results in a big sparsity problem. There are too many really for you to store in a table or a try. But they're systematic in how they're formed. So you can write an FST that will encode all of this information. Here is a finite state machine at the top in figure 3.3 that recognizes, in a shorthand way, English noun inflection. So basically, you hard code the irregular plurals and irregular singulars. This is usually actually easy because irregular forms are usually quite common. So you usually know about them. They're usually in vocabulary. And then for the regular nouns, then you have the noun root and then plural s. as transitions. Well, that just recognizes nouns. It doesn't generate them. It just tells you, is this a possible English noun? If you want to analyze nouns, then you can use an FST like figure 3.13, where you have regular nouns, and they get a plus n substituted for the empty string, and then either plus singular substituted for the word boundary, the end of word symbol, or plus plural substituted for the plural morpheme, morpheme boundary S, end of word symbol, that for regular nouns. And then for irregular singular nouns, you do a similar thing, but with the singular symbol and the plural symbol being substituted for the end of word symbol. Does this make sense? Oh, and the cool thing is, it's reversible. You can invert it. So all you have to do is reverse these, which of these is the input and which is the output with these symbols on each transition. And you run the same thing and it reverses. So you can do analysis and generation with the same FST just by inverting it, which is great. Another great thing about FSTs that I haven't mentioned so far is they're quite fast. So if they have particular properties, what's called deterministic FSTs, they actually execute in linear time, proportional to the length of the input string. For non-deterministic FSTs, then it's not that good. It's not as good as that, but it's still quite, the runtime is still quite efficient considering what you're getting out of them. So typically, you would divide a morphological analyzer into at least 2 sections, each of which is implemented with a separate FST. You'd have one FST that handles what's called morphotactics, which is how morphemes fit together. And basically, maybe how those morphemes map to a lemma or to a full analysis, a lexical form. So morphotactic FST would do things like map between zoch, noun plural, and zoch morpheme boundary S. So it basically concatenates the basic forms of the morphemes together. An important thing to know here is that the lemma can actually be guessed. So it can be an expression that could match any number of different strings. So you don't have to know the lemma in order to do parsing or in order to do analysis. So you probably want to mark it as a guess rather than as something that's in your lexicon. There are also allomorphic rules or orthographic rules. And these map between the output of the morphotactic FST, the intermediate or morphemic representation, and the surface representation. So this is what gets you from zoches to zoch, morpheme boundary S, word boundary, to zoches, Z-O-C-H-E-S. Does this make sense? This is actually very important to your homework. So if it doesn't make sense, now is a good time to ask about it. We'll go over it a little bit in a minute, a bit more. So you have one FST that puts stuff together, or that defines combinations of things. You have another FST that defines transformations of those things. So in terms of transformations, here are some examples. Here are some spelling rules of English. In your homework, you will implement all of these spelling rules, except for one that is already given to you as FST. So one is consonant doubling. So beg alternates with begging. So 1G here, 2G's here. We consider the one with 1G to be kind of the basic form, and to have a rule that doubles the consonant before ing and ed, before ing and ed. And likewise with the other rules here. So these are rules that you have to know in order to write English. And so our FST has to know these rules too. For out of vocabulary words, for words that are not in our lexicon. Is this clear? So what you're going to be doing, among other things, is writing FSTs for all of these rules. And here is what such an FST might look like. So this is the one for E insertion. After S, Z, and X. It also happens after CH and SH, but that makes it a little bit more complicated. So for teaching reasons, pedagogical reasons, then we just confine it to Z, S, and X here. You're actually given this FST to start with for the homework. And as an example, so you can see how this gets represented in the software that we're using, OpenFST. And then you'll write similar FSTs for the other. Now there's another way of representing the same kind of transformation, and that is with a rule notation like this. And this will be familiar to people who have taken linguistics courses, particularly phonology courses. Who here has taken a phonology course? Okay. Who here has taken any kind of linguistics course? Yeah, so here, a number of you. So here we have the empty string. Linguists would usually write 0 for this, or null set. But you have the empty string being rewritten as an E, so you're replacing nothing with E. When you're in the environment, so the slash means in the environment of either S, X, or Z, followed by a morpheme boundary, and when followed by an S, followed by a word boundary. So this is where the action takes place. This whole thing is the context after the slash, and the underscore is where the action takes place. So you don't need to know this really, except to know that when people are doing this in real life, when people are writing FSTs, they're not doing it the way we're making you do it. They're actually writing these simpler rules, and they're getting compiled into FSTs. But because we are mean people, and we want you to understand how FSTs really work instead of just having some high-level notion, which wouldn't be very educational, then we're making you write the FSTs by hand. What you really want to do, actually, when you're doing the homework, is you want to draw the FSTs, and then you can translate them into code. Basically, the code just has lines where you have the number for the start state, the initial state, following state, the input symbol, and the output symbol, separated by white space. And if you want to specify that something is a final state, which is what it means when you have the double lines around the state, the double circle means it's a final state. So to make a final state, then you just have that number on a line by itself. And that's basically all that there is as far as that goes. But that's still, it's harder than writing these rules. But we think you're up to it. So you can combine FSTs together. And this is something that in the next 2 weeks will be very important to you, we hope. So here we have a lexicon FST, one that handles morphotactics. Here we have orthographic rules. So we can go through these two FSTs to get from the lexical form to the intermediate form to the surface form, or the reverse. So if we go this way, we generate. If we go down, we generate. If we go up, we parse. But you don't have to, yes?
It says on the slide that there's multiple FSTs going on in the orthographic area.
Yes.
How are they selected from, or do you do them sequentially?
So in the textbook, when they talk about it, they combine them together through intersection. So, you know, you imagine these as relations. You're taking the intersection of all of these relations. There's a problem with that from our standpoint, which is that, as we'll talk about in a minute, FSTs are not closed under intersection. So OpenFST, the toolkit that we're using to do this, will not actually allow you to intersect FSTs, only finite-state automata. So we're going to do the equivalent thing instead sequentially. And when we're combining things sequentially, so here, you know, it looks like we're just feeding the output of lexicon FST into this set of FSTs and getting this. But what we actually want to do is to combine them together into one big FST. It's much more efficient, and it allows a kind of power that would not be possible otherwise. So it turns out there are a number of different operations you can perform on FSTs. The most important of these, for our purposes, are composition, concatenation, and union. So composition is basically equivalent to taking the output of one FST and feeding it as the input to another FST. Except instead of taking the output and feeding it to another one, you're just combining them together into one FST. That's composition. Concatenation is sort of stacking two FSTs end to end. So if you concatenate an FST that maps A to B and an FST that maps C to D, then you get an FST that maps AC to BD. Because composition is like feeding the output of one as the input to the other. So it's composition like in functional programming, or in it's like function composition. And concatenation, you're not feeding the output, you're just stacking the two transducers end to end. You're just having this transducer, then that transducer. So this is what you would use if you define an FST for guessing a lemma. And then you have FSTs for suffixes. Then you can concatenate the FST for guessing the lemma and the FSTs for guessing the suffixes. And you can get FSTs for the whole inflected form of the word. So the other important thing for our purposes is union. So you'll use union a lot in your homework. And union means that given two transducers, you have another transducer that includes all of the tuples in both of those relations. So that everything that would be okay with transducer A and everything that would be okay with transducer B are okay with our new transducer C. So it's a kind of parallel thing. So people often ask me in class, how do you do composition? And I tell them, well, there's an algorithm that you use to do this. And it's like, well, no, can you show me on the board how to do composition? I said, well, I don't know the algorithm by heart, but you can look it up. And they said, no, what is the algorithm for composition? So I'm going to show you. Anyway, this is the algorithm for composition of finite state transducers. This is actually a little bit more complicated than the one that would be, than the simplest one that would be possible for normal finite state transducers. This is actually for weighted finite state transducers, which are a generalization of vanilla finite state transducers. So this is how you can imagine FST operations working. You have the lexicon FST, you have the orthographic rules FSTs, the allomorphic FSTs. So you combine these together. They use intersection. We're going to use composition. And so you have lexicon FST, allomorphic FST. Then you compose the lexicon FST and this other FST and get a singular big FST that does everything by itself. So you can write things in little pieces, and you can put them together and make big things out of them. You write them in little pieces that are easy to test and easy to understand, and then you can compose them together into, compose them and union them and concatenate them together into bigger, more complicated structures. Let's get that. I want to go on to some notes on homework 2. Because I want you to do well on homework 2. It's a new homework, and we've spent a lot of effort in making it good. It's hard, so we're giving you 2 weeks. I mean, it's a lot of work, I should say. It's not super hard. But this is basically what you'll be doing. Instead of doing analysis, where you give all of the properties of a word, the lemma and the properties, that would be analysis. You're just going to give the lemma. So given the inflected form of the word, you're going to give us the lemma. And given the lemma, you're going to give us all of the inflected forms of the word. Because it's invertible, right? So it's no extra work to do that, if you did a good job, which you will, I'm sure. So you'll do lemmatization. So squig, squigging, squigs, and squigged should all map to squig. So you'll do this in 3 parts. So first, you'll implement delemmatization for in-vocabulary words. So you'll make a transducer from lemma to surface form for each. So you'll be given a vocabulary. And you'll make a transducer for each lemma inflected form pair. You'll make a transducer. And then you'll take the union of, and you'll do that programmatically because there are like 10,000 items. So you're not going to do it by hand. You're going to write a program to do this. And you're going to take the union of all of these transducers, and you'll get one big transducer for the known vocabulary items. So that's taken care of. Easy peasy. Then you'll implement morphotactics for out-of-vocabulary items. So you make a transducer, one transducer for each affix. That so you'd have the recognizer for the lemma, and then the transducer part that adds the affix concatenated together. And you'll make one for each of the affixes. So for ing, for ed, for s, for nothing. And then you'll take the union of those. Then the hard part is you'll implement orthographic rules for out-of-vocabulary words. So you'll make a transducer for each rule from the intermediate or morphemic form, and then you'll compose them together with a post-processing FST that removes the word and morpheme boundaries. So you'll do all of this manipulation where you need that word and morpheme boundary information, and then you'll get rid of the word and boundary information. You'll concatenate all of those together, and then you'll compose FST2 and FST3 to be one big out-of-vocabulary FST, and you'll take the union of that FST and FST1 and have an FST that does delemmatization. That basically, given a lemma, gives you all of the inflected forms. Then you will invert that FST, and you'll have an FST that does lemmatization. Questions? Who is totally confused? You can admit it. Okay, you're totally confused. Me too. I'm confused as to why you'd be confused. No, just kidding. So questions? Yeah.
So what exactly do you mentioned that for FST1 will be using
Yeah.
for FST2 and FST3 are we expecting those rules?
So you'll be given, you have a list of rules for FST3, which is in the textbook. You may want to refine those beyond the definitions given in the textbook to improve performance. But the orthographic rules will be these in the table that's labeled English spelling orthographic rules. So you'll implement each of these rules. So for the morphemes, these you can get by looking at the in-vocabulary data and figuring out the patterns. And they're very simple. You know, you concatenate ing, you concatenate ed, you concatenate en, you concatenate s, you concatenate the empty string. So if you want like that in writing, then post on Piazza and we'll write it out to make sure that you don't miss anything. So other questions? I know there have to be other questions. Yeah. So in vocabulary, for our purposes, so you're given a list of words, and they're inflected forms. And if it's in that list, it's in vocabulary. If it's out of that list, it's out of vocabulary. Yeah, but you'll be given a list of 10,000 words. It was supposed to be 100,000, but Gradescope can't handle an FST that large, apparently. So, so it's 10,000 words instead. Yes.
parse up and do the transducer.
Yes. And if you have any questions or need any help with that, then post on Piazza and we'll hook you up. Yes.
When you perform inversion, do you need to understand the state of the FST from start stage onto?
What do you mean by understand?
If we imagine the FST as a bunch of nodes in a graph, do you need to know which path to traverse through this graph?
No. So what you need to know is, so the FST just describes a relation. And it doesn't have a history. It just corresponds to a pairing, a set of pairs of strings. And so all inversion is, and all you have to understand inversion, is that the order of those pairs is switched. The sequence of the items in those pairs is switched. You don't need to know anything other than that. And all you do to invert an FST is actually switch the labels. Yes. Yeah, it's easier. You could do it the other way, but it's easier to think about the orthographic rules going from the intermediate form to the surface form rather than going the other direction. So it's simplest to write those applying downward, we say, and then invert them to apply upward. It's just easier to write it that way. But there's no reason that you can't do it the other way as well. You know, it's equivalent, ultimately. It's just a little bit easier to get your head around. Yeah.
There is a slide called the inversion rule for the FST.
Uh-huh.
Again, highlighted.
Right. So this is an FST implementation of the E-insertion rule. It's not exactly the same as the one that you'll be given, but it's very similar. So the idea is that you feed this a string, and if it's a string like the word buzzes, let's say B-U-Z-Z-E-S. Okay, so, or if it's a string, basically it would be buzz morpheme boundary S. Okay, so you've got buzz morpheme boundary S. So we look and see, is there a path through this FST that transduces buzz morpheme boundary S? So if we start here, then if we start at Q0, then we can see that there's an outgoing transition for Z and S and X, but not one for B, but there's a loop with other. So that will accept any other, any label other than, or that will stands for any label other than the ones that are explicitly specified. So we go B, U, and then we have Z to Q1. And then we have another Z, so we take this loop back to Q1, and then morpheme boundary over to Q2. And then what's going to happen is we're going to insert the E between Q2 and Q3, and then we transduce the final S as an S, and we get to Q4, and then there's a word boundary at the end, so that gets us back to Q0, which is the final state, or an acceptor state. So that means that buzz morpheme boundary S has been transduced to buzz ES. So what if we take another word? What's another good word? Maybe that ends in S. That doesn't. So let's say bugs. As in, that question bugs me. No, just kidding. It doesn't. So you have B back to Q0, U back to Q0, G back to Q0, S to Q1. Then we're at the word boundary, so we go back. We can only go back to Q0. So it accepts bugs, but it just returns bugs. Bug morpheme. Well, it would be bug morpheme boundary S. So, but it works the same way. So the that's what that slide is about. And you'll become much more familiar with this concept by the end of 2 weeks. What? There's actually a mistake here. I don't remember what it is, but last semester, then we found a mistake in it.
So my question is, for the last transition, we have the S. Is that actually the end strand colon S?
So when you have just S like this, it's S colon S. So it's rewriting S as S. So that's a shorthand for S colon S.
And then that goes for the Z, S, X.
Yeah, that's Z colon Z, S colon S, X colon S. Other questions? These are good questions. Yeah.
So, for example, the way to like box sharp, so it will just return box sharp. And then like to get the original word, we have to remove this one.
Yeah. Yeah.
So that goes for like every other word. After transformation, that was the last one.
Right.
So why don't we just leave that symbol in here?
Well, because, well, they talk about that in the caption there, but sometimes, so it depends on whether you're intersecting the rules or concatenating them. If you're, or rather composing them. If you're composing them, you don't want to get rid of the word boundary at the end of the thing because you want to still have that information for the next rule that comes along. If you're intersecting them, then you can just get rid of it. You can just rewrite it as epsilon. Does that make sense?
Yeah.
Other questions? Okay, so let's finish up with a brief discussion of stemming. So sometimes doing morphology, real morphology, is too hard. And you're tired, it's the end of the day, you just need something to work, you're doing information retrieval. You can do something called stemming. And stemming basically takes a word and outputs an approximation of a word stem. And by stem, in this case, we mean not what a linguist means by stem, which is like the root plus all of the derivational affixes. It's a string such that all forms of the word have the same string, and words that are different have different strings. So you usually do this by just doing substitutions at the ends of words, in English at least. And here are some examples from Porter's stemmer, which is a widely used stemmer. There's also snowball stemmers, and a lot of this stuff is built into NLTK. If you've heard of that, a lot of people will use it in their projects for doing things like tokenization, and perhaps stemming. So it's something good to know about. Linguists tend not to think very highly of stemming because it gives results like this that are very noisy. So here is the input word, here's the output word. And nobis and noble both end up having the same stem. Noblemen and noblemen have different stems. So it's not very, these algorithms are not very smart. They just change things at the ends of words. And, but for some things, they're good enough. Also, there's the subject of tokenization. So tokenization is when you divide text into tokens, into word-sized chunks. So the input is raw text. The output is a sequence of tokens that are normalized for easier processing. So all of you in your projects will have to do this to the data. You'll have to, and probably you'll outsource it to some toolkit, like NLTK. So tokenization might seem easy, right? You just split the words up based on the spaces. Done. But it's actually a lot more complicated than that. Even in, there are a lot of languages where there is no white space. Like in Chinese, you can't tokenize on white space because there's no white space between words. It's easy to divide into characters, but it's not easy to divide things into words. And Thai, utterly hopeless. It's true. But even for English, this is hard. So how would we tokenize this text? Dr. Mortensen said that tokenization of English is harder than you've thought. When in New York, he paid $12 a day for lunch and wondered what it would be like to work for AT&T or Google Inc. So tokenizers usually treat punctuation as separate tokens. That's one thing to know. So what problems do you see? What challenges do you see for tokenization here? Yes? Yeah, you've is actually really kind of two words, and you probably want to tokenize it as two words. But by white space criteria, then it's one word. Yeah. Yeah, often you'll want things like New York to be one token. And yeah.
Just $12. How do you even feel about that? Is the dollar sign a separate word? If so, is like the symbol good enough? You count the dot to a lot of.
Yeah. Is the dollar sign a token? So normally when it's punctuation, when it's end of sentence punctuation, a period is a separate token. But sometimes it's not so easy. Like in $12, should it be a separate token? Probably not, because it's part of a numerical expression. But it's complicated, and you have to choose what is going to work best for a particular application. So what about Google Inc? What's hard about this? Should be one probably, but if we're doing this in a naive way, what is it going to do to the ink to the period at the end of ink? It's at the end of a sentence. So it should be a separate token, right? It's end of sentence punctuation. But it's part of the abbreviation incorporated, too. the abbreviation Inc. for incorporated. Yeah. What? Well, you have to choose. So probably you want to tokenize it as part of Inc. or as part of the abbreviation. So usually abbreviations, so periods at the end of abbreviations get tokenized as parts of the abbreviation. But it's confusing to any kind of heuristic or rule that you want to write for tokenization because it is at the end of a sentence. So how does, so you have to know all of the abbreviations in advance in order to know when an end of sentence period is part of an abbreviation and when it is end of sentence punctuation. So tokenization is actually hard to write a good tokenizer. It's not very sexy. You know, it's not like there are shared tasks in tokenization, but it's something that impacts every aspect of NLP when working with text. You can't do anything really without tokenization of some kind. You know, with any model, you have to choose how you're presenting the data to it and how you're doing pre-processing. And an important aspect of this pre-processing is tokenization. So with that in mind, enjoy the brief respite that you have between this class and the onset of the new assignment. Are there any last questions about homework 2 or about this lecture?